welcome back. Ugh, wow, these are long, I know, so I apologize. But hopefully I'm helping you to get the trick of how to actually use the machinery, the mathematics, in order to realize these particle dynamics without using perturbation theory, without using QCD, without using QED, without using the standard model, yada yada yada, but under the understanding that we can show that these vertices actually can be associated with the bits of particles and matter that we've observed in the laboratory. And that one way that we can literally understand that, yes, these are the bits of matter we've been seeing in the laboratory is, do they transform? Do they react and form the things that they should form from the laboratory? Do they have the same reactive properties under what we are now calling our evolution equation or our similarity equation? Now, just as a brighter physics way of thinking about it, the transformation matrix that we're talking about, the T matrix, this orthogonal matrix, is in point of fact what we would call, or will call later on, the Hamiltonian of the system. It is the time operator. It is what enables us to go from a state at some, where we've mapped out the spatial positions, to another state where we've have different spatial positions, where things have changed their locations, okay? And in the process of changing their locations, they've also changed how they are structured to each other, how they relate to each other. So also later on, we're going to get to the idea that the edges that actually connect vertices are what profoundly are called entanglements. So spaces, literally when we map out a frame and call it chi, and call it a graph, and call it a space, because we've defined all of the vertices, we know all of the possible locations that things can exist in on the space, then what we're really talking about is a film frame, a literal snapshot where the time is it's at a single moment in time. So we can talk about how things interrelate with each other at a single moment in time. And the only way that things can interrelate with each other at a single moment in time is if, and only if, they're entangled. Relativity says it cannot happen. Quantum mechanics says it must happen. And since we know that quantum mechanics is superior to at least in terms of its underpinnings, to relativity theory, then we know that we can talk about a space in which there is no time, where the vertices are connected, they're linked to each other. And the very definition of that link in that space is what we would today call entanglement, that those two vertices are entangled. In other words, they exist beyond time. There is a connection that they share beyond time. And so the whole notion of what is an edge is an entanglement link. And we're going to get back to that. But time in this theory is a Hamiltonian operation. It literally walks you, a moment, a unit of time, a chunk of time that has passed, happens when the Hamiltonian operates on you. And as we've seen here, our Hamiltonian, our transformation matrix, is not only orthogonal, but the parameter, the one parameter, in this case theta, that we've used was 45 degrees. So it seems like the time is not continuous, that it is as discrete as the space is. And, that happens more or less. We'll talk about that later. But for the most part, at least with a two-vertex system, our time operator is, in point of fact, a discrete operator. Literally, you walk through units of time and chunks of time. It's kind of cool. But we can see that up front in the theory. So what I did want to explore in this little segment, as I tried to talk about before, is the neutrino. And how we've come about to the idea that, That thingy that we came to last time is the neutrino. We'll get to that. So what we're going to do is we're going to start with how we know, or what we know the neutrino interacts with, how we know the neutrino is there. So we define the neutrino from before as this particle, the electron-neutrino specifically, as this particle that when it interacts, when its antiparticle, the antineutrino, interacts with an electron, it can form a W minus particle. So you remember that? And then what we did was we rearranged the equation. And eventually, when we rearranged the equation, we came up to the idea that the W minus, that a W plus, the anti-version of the W minus particle, plus an electron, must produce a regular electron-neutrino, that this reaction should exist. That's what we've come up to. So essentially what we're saying is, if you take an electron beam and you take a W plus beam and you fire them at each other, that there's going to be a reaction rate, that there's going to be a production of electron-neutrinos with a reaction rate. So you're going to see that some of these particles are going to combine and form these other particles, blah, blah, blah. But nevertheless, the way this comes about here is the electron given by that structure, and then the W plus given by this structure. Okay? So those are the two structures that we have right here. We're going to label this one 1 and this one 2. And now we're going to formally write its matrix. And remember, guys and gals, how we write that matrix. Okay? So our 3 connected electron has a +3 here. And our, and this is one that we haven't tackled before, but this structure here has 2 lobes, or 2 loops, and one arrow. This one arrow is a minus. These 2, each one of them is a +1. So together, you have to add them all together. And when you do that, you get a +1. So this becomes a +1 here. Okay? Now, because these 2 particles are in fact not entangled, they're not linked by any edge, that's a 0. What would exist from 1 to 2 is 0. And so that's what goes here, and that's what goes here. Because also it's from 2 to 1. Nothing. Okay? So the matrix that describes the electron and the W plus is this. Now what we want to do is we're going to do something slightly different. We know that, that our transformation equation, T transpose chi1 T, right? That equation should give us a new chi, and we're going to call it chi2. Now, from our previous work on the electron-positron to a photon, on the the pi meson UU bar to the pi meson DD bar, that we're just going to make a little faith-based effort and basically say that we're going to use the same transformation matrix, the same Hamiltonian, which was basically a 45-degree, the parameter was 45 degrees. So if you recall, I'm not going to go back through what the transformation matrix is, but if you recall, that matrix came out to be 1 over the square root of 2, 1, 1, minus 1, 1. Remember that? Okay? So we've used that same transformation matrix, so that same Hamiltonian in all of those other situations. Now we're going to apply it again and see what happens. Why not? So our T transpose is just that, flipped by the diagonal. I'm just going to write that out. T transpose is 1 over the square root of 2 times 1 minus 1, 1, 1. Okay? So these are the forms of the T that we're going to use. Now, let's do the multiplication. I'm just going to take the 1/2 already out, so we don't have to go through that process of bringing it out and writing all of that out. Okay? So this is what we're multiplying. Okay? So we've got our T transpose here. Did I get that right? Nope, sorry. Got that wrong. Let's just reverse the signs. Okay. So we've got our T transpose over here. We've got our our electron and our W plus here, and we've got our T here. Let's see what that equals. So we're going to multiply the first two parts together, and the first two matrices together. We're going to get 3. We're going to get -1. We're going to get 3. And we're going to get 1 for the first two. And we're going to multiply that by the last matrix. Okay. So the first two here give us this. Give us this right here. And then that last matrix up here gives us this here. So we're now going to multiply these two together and see what happens. So we get 3 plus 1, which is 4. Right. Yep, 3 plus 1 is 4. And then we get 3 minus 1, which is 2. And then we get 3 minus 1, which is 2. And then we get 3 plus 1, which is 4, all times 1/2. Right? That's what that is right there. That's all three of those multiplied together gives us this now. And then we just take the 1/2 and multiply that through. And we get 2, 1, 1, 2. Oh my gosh. We get that. Now let's draw this. Okay? Let's draw this out. Let's make this into a graph. Because all we've done before is to take the graphs and make them into the matrix. Well, the claim certainly is that you can take the matrix and make it into a graph. And we've done that as well. So let's make this into a graph. So we've got 2 vertices. Okay? And on the first vertex, there has to be 2 loops, because that's what the +2 means. On the second vertex, there also has to be 2 loops, because that's what the +2 means. And between them, that is, between 1 and 2, we find that there's a 1 here, and there's a 1 up here, right? So there's only one edge that connects them right here. So put in an edge. So this structure is, in point of fact, this matrix, which basically says that when you put the electron together with this W plus particle, then you get this other structure, which absolutely now must be a neutrino, an electron-neutrino. That's the key. So now that we're able to write out particles, I'm just going to rewrite this out for you in terms of the graph. Okay? And also in terms of what it represents in terms of particles. And also in terms of the matrix representation. Okay? And then we can see how our matrix math actually comes out with particle magic. But it's not really particle magic. We're actually demonstrating that the particle reactions really are borne out when we ascribe certain particles in certain ways to the particles that we actually see in nature. Now, certainly what we find here is something very strange, right? We've got this entity that on the one vertex has two lobes or 2 tadpoles, and on this vertex has 2 tadpoles as well. So the overall number of tadpoles that we have is 4. Now, if you remember from our initial way of describing what a particle is, or rather, why an electron is an electron, why we ascribe this thing to be an up quark and that thing to be a down quark, and yada, 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 and blah, 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 thank you, Seinfeld. But, you know, when we go through all of that identification, we were able to also show that the reason why we assign this to a U quark, or an up quark, is that it looks like it has 2/3 charge. And when we assign this to the down quark, it looks like it has a 1/3 charge. And when we assign this to a bit of energy, it absolutely looks like it has no charge because of the number of loops that are there. I'm actually just trying to dig out the diagram that shows all of that, but I seem to not be able to find it. Here it is. Yeah. Here it is. All right, give me a second. There we go. Nope, that's not it. Okay. So in the physics world, this is what happens all the time when you are doing a lecture offhand from scratch with no real lecture notes. So it's buried in here somewhere. I just wanted you to see the diagram once again, but you know the old adage of when you want to find something, you can never find it, and when you aren't looking, it all of a sudden appears. And I'm almost certain that we will be able to pull that that particular razor out of this theory, and we'll just call it the PhOENIX razor. Thank you, Occam. Okay, now, so all I was just demonstrating here is that we can represent the particles, the identified particles, with both graphs, visualizations, and with their matrix counterparts. With the matrix counterparts, we can demonstrate that they can be transformed into each other using a similarity equation where the transformation matrix is in point of fact an orthogonal matrix, and where that orthogonal matrix, especially in the v equals 2 case, is a single parameter, and that single parameter is a discrete parameter. So what we haven't demonstrated is that that parameter can run basically 45 degrees, so 0, 45, 90, 135, you know, you get the picture, 180, 225, etc., all the way around. You can run that parameter discretized by 45 degrees and demonstrate that you get all of the gnarly particle reactions that can exist at a v equals 2 level, a 2-vertex level. And you can get these, this is a leptonic reaction. Okay, so we know that this entity here is a lepton. Now notice that when we had identified this thingy here, this particular type of vertex, which I showed you looked like, well, it looks like that, but I wanted to give you my little card routine, this thing right here. There. Okay. So when I showed you that, I said, that's a quark. But remember when I said it was a quark-lepton methodology? So what I really meant in that is that in some circumstances, it behaves like a quark. But in other circumstances, like right here, it doesn't behave like a quark at all. It behaves like a lepton. It behaves like a leptonic structure. So when two of these things come together, you get a leptonic structure. So when you go back to QCD, or quantum chromodynamics, and you actually look at the structure of the theory, and you look at, you know, can you take a U quark and combine it with another U quark? The answer is no. Those two things are forbidden. That combination does not exist. You can, however, combine a U quark with an anti-U quark and get a meson, or you can combine a U quark with a D quark and another U quark, or you can combine, in other words, you can triple it. You can combine a U quark triple-wise, but you can't combine it double-wise. Well, here we have demonstrated that this thing that acts like a U quark in QCD acts like a leptonic structure also in this theory. So acts almost like a QED structure, or exactly like a QED structure. So that when these two things, these alike things are brought together, they form a lepton. The same thing happens, by the way, when you bring together the D version of that. The structure that we get there, however, is a little different, and we'll speak to that later on. But that structure is definitely leptonic. And that structure speaks to the idea of, what if we try to bring together a W and a W, right? So what if we tried to bring together, let's say, a W and a W. Okay. We're going to get possibly a piece of leptonic matter that has a double charge. So it's a double E2 or a double E minus 2. You know, this theory accommodates that. And this theory basically says that when you look for something like that in the laboratory, you're really looking for a very, very, very high energy particle, because what you're doing is you're bringing together two W's. This is no longer just an electron interacting with a W. Now you're bringing together two W's. So this new particle, this new lepton that's formed, this doubly charged lepton, is in point of fact an extremely high energy particle. So I just wanted to put that out there as one of the predictions of this theory. but can only be explored when you get accelerators that are probably what we could have achieved with the superconducting supercollider in Texas, but we'd never built, and may not be able to achieve with a collider at CERN, the Large Hadron Collider, simply because there's not enough energy to bring those W's together to find the signature that we would need to see for this doubly charged lepton. Okay, so what we've, again, demonstrated was how to use the mathematics in order to have a neutrino creating an electron and a W plus, or W rather, and having a photon being created out of an electron and an anti-electron, and showing how the UU bar pi meson oscillates into the DD bar pi meson and back and forth. Now, I'm going to end this particular one, and we're going to talk a little bit about a new type of matter that the theory absolutely predicts, and we're just going to talk about it a little bit. Okay.